Welcome back to Algorithmic Game Theory. Last time we started talking about the question, how well can prices coordinate markets? This means that rather than running an auction, we now want to, for example, in a combinatorial auction, we would rather want to post prices to the different items so that buyers get their favorite bundles, and at the same time, social welfare is at least approximately maximized. And what we got to know in this context last time was the concept of a Walrasian Equilibrium, which was exactly this choice of prices and an allocation, such that every buyer is happy with what they're getting. So no buyer would rather want to get a different set. Today we are complementing this with a more modern theoretical approach, which again posts prices, but now the buyers just come one after the other and they take their preferred set. And as we see, this does make a bit of a difference. Then our welfare guarantee we will still prove a welfare guarantee, but we won't be able to show that we get optimal social welfare, but only approximately so. But at the same time, we work with less information. So I hope you see that there are many similarities, but also differences. What is the precise model that we're talking about? Like in a combinatorial auction, we have n buyers. That will be the set capital N, and we will usually call them just 1 through n. And we have m items. And each buyer I in n has a private valuation function Vi, which again assigns a non-negative real number to every set of items. And we assume that these are unit demand functions. That is, Vi of S will be the maximum of all j in S Vi, j for non-negative Vij. In other words, every buyer can in principle be assigned multiple items, but if they are assigned multiple items, then what they care about is only their most valuable one. Good. Now, as you see, there's already something different here compared to what we were talking about last time, namely, these valuation functions are assumed to be private today. They are not public knowledge as in the theory of Walrasian equilibria. But we again make the assumption that we also made in the context of Bayes-Nash equilibria that in advance we know probability distributions which these valuation functions are drawn from. This means Vi is drawn independently from a distribution Di, and that will be a known distribution. But other than that, we make no further assumption. So once again, these are known, but the valuation functions are private. And now we'll study the following kind of a mechanism. We first compute item prices. So a price Pj for every item. And we do this based on the knowledge of d1 through dn. And then we approach the buyers in order 1 through n, and each buyer I buys whatever set Si maximizes Vi of Si minus the sum of the prices in Si and pays the sum of the prices. Good. So what's the mechanism? It's really simple once you know how to do this first step. In this first step, we somehow, and that's something we have to talk about, we somehow compute these prices, one price for every item, and then we put a price tag on every item. We do this based on knowing these distributions. Of course, we don't know the valuation functions because those are private knowledge. And then we approach the order, the buyers in order 1 through n, and then each buyer chooses whatever set Si maximizes this buyer's utility. So Vi of Si minus the sum of the prices in the set Si and pays the sum of the prices for the set that they chose. This you could also express as an allocation function f, as an allocation rule, or outcome rule as we call this, for a mechanism for every fixed d1 through dn. And then you also have a payment rule. The payment rule is also easily described. But that's maybe actually even a bit misleading because the way agents now perform, or the way agents behave here, is not that they're telling us, okay, this is my valuation function, give me something, but they rather choose whatever they prefer among what is left. The reason why I state it this way is that now it is completely obvious that this is a truthful mechanism. How so? Well, why should I misreport, or what are my alternatives? I could buy a different set. When it's now my turn, I could simply choose a different set. But would this make me happier? Of course not, because I'm just choosing the set whichever maximizes my utility. So choosing a different set, lying about my valuation, saying that another set makes me happier, there's no point in this. At the same time, while truthfulness is easy, now of course this comes at the price that we now have to know these distributions in advance and that we have to fix the prices, which, for example, a mechanism like VCG could do without. But let's first write down this. observation. And it says that the posted prices mechanism is truthful for every choice of the prices. Now what we want to know is, how much welfare are we getting this way? If we choose the prices appropriately, how much welfare will we be getting? And we won't be getting the full optimal welfare, but we will get close to this. But how should you choose the prices? Maybe one thing that you might try is take the Walrasian prices. Let's just assume that the distributions D are such that we actually know the valuations in advance. And then we might just choose a Walrasian price vector. Will this then result in a good allocation or not? Unfortunately not. Why that? Or let me say it, not necessarily this will be a good allocation that we end up in. Walrasian prices are not necessarily a good choice. I have now 2 buyers and I have 3 items. And the values are as follows. I have a value, the first buyer has a value of 1 for the first item and a value of k for the second item. The second buyer also has a value of k for the second item and a value of 1 for the third item. What could a Walrasian equilibrium look like here? We might set the Walrasian prices as follows. And we would then consider, for example, that the allocation that the first item goes to buyer 1, the second item goes to buyer B. This is a Walrasian equilibrium. There's another Walrasian equilibrium in which buyer 1 gets the second item and buyer 2 gets the third item, but the prices will be the same. But what happens now if the buyers arrive in order 1 and then 2? Well, the first buyer arrives, and this buyer now has the choice between item A for a price of 0 and item B for a price of k minus 1. Which one do you prefer? Which one maximizes your utility? Well, I'm indifferent, because here I'll have a utility of 1, and here I'll also have a utility of 1. The same is true for the second buyer. Also, this buyer is indifferent between item B and C. So one thing that might come out of the posted prices mechanism is that buyer 1 takes item A and buyer 2 takes item C. This could be an outcome. And then we have a welfare of 2 as opposed to k plus 1. The first buyer might take item A, and the second buyer might take item C. And then we get a welfare of 2, whereas the optimal welfare will be k plus 1. So if k is much bigger than 1, then we are very far apart from the optimal welfare. And once again, what was the reason? The reason was that the players were indifferent between the options that they have, and this is indeed one of the main principles of a Walrasian equilibrium, that people tend to be indifferent. And so this is not exactly what we're looking for here, especially when we're then moving to the setting of incomplete information. Then all these Walrasian prices won't take you where you want to go. Instead, what we'll do is we will state a way to design much more robust prices, which don't guarantee us optimal welfare, but at least we will be within a factor of 2 of the optimal social welfare. The first step that we want to now do is just understand how we can define much more robust prices for the case of full information, so we actually know these valuation functions in advance. As we've seen, Walrasian prices don't do the trick because of these issues of tie breaking, but there is a different and very easy way of doing this. We'll set a price of 1/2 times Vij for item j if buyer I gets item j in an optimal solution on the valuation profile V, and 0 if item j is unassigned. In an optimal solution on valuation profile V. Okay, so once again, what are we doing here? We assume that we know these valuation functions all in advance, and now we define prices, and to indicate that we know this valuation profile, we'll write a superscript V now to the prices. And we say, okay, what's the price of item j? Maybe nobody's getting this item in the optimal solution, the social welfare optimizing solution on valuation profile V, then we don't give it any price. Otherwise, then let buyer I be the one getting the item in the optimal allocation, then the price will be a half times Vij, where once again Vij was buyer i's value for item j. And to now understand what is happening there, we'll first introduce some kind of weird notation that then lets us very easily understand the outcome of our mechanism. Namely, we let opt subscript I of v be the item that buyer I gets in an optimal solution on V. Good. So here we use that these valuation functions are unit demand. So in our optimal solution, in our optimal allocation, I might want to say, each buyer gets only one item. And let's now write this as opt subscript I of V. And maybe you're now asking, what if buyer I is not getting any item? Then we can just set this, for example, to 0. Now, there is a somewhat weird way of writing now this price Pj superscript V. Namely, we can now take a half times the following sum, take the sum over all indicators, whether opt subscript I of V is equal to j, and then multiply this with Vij. What does this mean? This here, this is 1 if opt I of V is equal to j and 0 otherwise. Why am I writing it this way? Because this will be helpful later. First of all, you should see, okay, this is actually expressing exactly the same thing. If the item does not get allocated, then all of these indicators will be 0. If the item does get allocated, then one of these indicators will be 1, and then we're taking the respective Vij. Okay. So once again, what are our prices? Buyer I gets item j, then we take half the valuation that buyer I has for this item. And this will be our price. How do we now understand the outcome of our mechanism? We'll first now see what will now distinguish is which of the items do get sold. Of course, a subset of the items will now get sold in our mechanism. And for those, buyers pay something, and whatever they pay is at least whatever value they have for these items. So this already gives us one way of lower bounding the social welfare of our outcome. More precisely, we now do this as follows. We let T subscript I of V be the set of items sold to buyers 1 through I. The revenue of the posted prices mechanism, so how much are the buyers paying, take the sum over all items, take that item's price, and now multiply it again by an indicator, namely, is that item in the set Tn. So is anybody up to player n buying this item? This we might alternatively write as take the sum over all buyers, whatever is the item that buyer I is getting in the optimal solution, and then multiply it by the indicator that this item is indeed sold. Okay, so this is one part of our social welfare. One part is the revenue, and the other part is the buyer utilities. So this is something that we've seen multiple times so far. We can also express the social welfare of any mechanism as the sum of the utilities plus the revenue, so the sum of the payments. And what do we know here about the utilities? And that's now actually the trick that makes all of this work. Because the utility of buyer I will be at least 0 because buyer I could always buy nothing. And there is another option that buyer I has, namely, if the item that this buyer is getting in the optimal solution has not been sold by that time, then buyer I could also buy item opt I of V. This gives us that the utility will be at least the value that this buyer has for this item minus the price of this item. And then we have to multiply this with the indicator that this item has not been sold when buyer I arrives. Now this is of course lower bounded by the same thing, but now multiplying this with the indicator whether or not the item is sold eventually. Because this is the same, but this here, this term, this indicator, this is 1 if the item is not yet sold after buyer I minus 1. This is the indicator whether the item is not yet sold after buyer N. So this here will be at least this much. Okay. And now, how do we get the social welfare? We just add all of this up. We add the revenue and the sum of these utilities. So our social welfare will be the revenue plus the sum of the utilities. And we now plug in both these bounds. What was the revenue? What was the revenue bound? It was this up here. Once again, we just get for every item opt I of V, we get the price whenever it is sold eventually. And then we should also take the sum of the buyer utilities using the inequality that we derived. And now, let's see how this all fits together. Well, this here is how much? How much is buyer I's value for item opt I minus the price for item opt I? For this, we once again have to go back to how the price is defined. Okay, the price that buyer I has for item opt I, this is exactly, or that everybody has for this item is exactly half the value of buyer I for this item. Because now here J would be equal to opt I, so this will be a half times VI, comma, opt I. So this will be V of opt I of V minus a half times VI of opt I of V, which is, again, a half times VI, comma, opt I of V. So this is indeed, again, the price. Which means that if we combine this, then we're getting, take the sum over all buyers, and then take the price of item opt I of V, and then multiply this with two indicators, namely opt I is in V, opt I of V is in T of N, is not in T of N. Yeah, now depends. The point is we get both these indicators. We get the indicator that it is not in Tn and that it is in Tn, and so the sum of these indicators will always be 1. So what we're ending up with here is just the sum of the prices. And this is indeed exactly equal to half the optimal social welfare, just because this is what we started from. This was the sum of the prices is exactly a half times the optimal social welfare, because each of the prices was just based on who's getting the item and then how much welfare, how much value does this item give us, or in other words, how much does this item contribute to the social welfare, to the optimal social welfare. This is indeed our price. And this is exactly what we were claiming. Now this is easy, and in the second step, what we'll do now is we'll move to the setting of incomplete information, which works just the same way, only that everything is written inside expectations. Now we come to the setting of incomplete information, so rather than knowing the exact valuation functions in advance, we only know the distributions that they are drawn from. And the prices that we've used so far, this was this PJ superscript V, and we will reuse this, so that's why we have again the definition here. We set a price of an item. If we knew the valuation function, we would, or all valuation functions, we would set the price of item J to have its contribution to the optimal social welfare in valuation profile V, and 0 if it doesn't contribute anything, of course. Good. Now, how do we get to prices that work in the context of incomplete information if we know only the distributions? Well, we do something which eventually feels almost a little obvious to do. Namely, we do the following. We take the price, the expected prices that we're getting this way, where now V tilde is an independent sample from our distributions. So we don't know these valuation functions now, but we know the distributions that they are drawn from. So let's draw from those distributions. Not only once, but twice, 3 times, many times, and always see what would the prices be. And now just take the average of all of these. Or in other words, what we're doing is we're taking the expectation of the prices where that we would now get where if we drew from the distribution D1 through Dn a valuation profile V tilde. V tilde, this has nothing to do with the actual valuations, except for that it is drawn from the same distributions. But V tilde doesn't actually show up in the final mechanism anymore, because the prices, they are no random variables, they are deterministic. They are just the expectation of the prices in this random experiment. And what can we show for this? This is a result by Feldman, Gravin, and Lucier from 2015. which is the expected social welfare of the posted prices mechanism is at least a half times the expected optimal social welfare. So we can again interpret this as kind of an approximation factor, if you like. We are within a factor of 2 of the optimal social welfare via this mechanism. The optimal welfare we would get, for example, if we ran VCG, which is more complicated than what we're doing here. At least for the buyers, it is more difficult to explain because here the buyers just see whatever items we're offering and then they just take their favorite items, as opposed to in VCG where they actually have to tell us for every item how much they value it, and then we take the information of all of the buyers and then we come up with an allocation and payments. Here this is much easier. Buyers don't have to all show up at the same time. We just give them something one after the other. And we're still within a factor of 2 of the optimal welfare. Our goal is now to prove this theorem. And how will we do this? We will mostly do it the same way that we proved the same kind of a result for the full information setting, except for now everything is inside expectations. And it's not quite as easy as this. It's not just writing expectations around everything, but this is more or less what will be happening now. So, more concretely, let's first talk about the revenue of our mechanism. What will the revenue be? I'm now reusing all notation that we were using before, and this is actually something that holds just as before. Take the sum over all prices, or take the sum over all items, and then always multiply the price with the indicator whether this item now gets sold when the valuation profile is V. So, what does this mean? This also means that in expectation, what will the revenue be? We can use linearity of expectation. Don't forget that the prices are actually no random variables. Those were defined as expectations themselves, but we don't care at this point. And we get here. This expectation of an indicator you could also write just as a probability. This is exactly equal to the probability that item J is sold eventually. But it is easier for us to keep it this way because then later we will again do the kind of a trick that we have 2 indicators, one of which will always be 1. Now we'll have to talk about again about the utilities of the buyers. What will the utilities of the buyers be at least? And now we're doing something to bound this that we've also used for to bound the price of anarchy of Base-Nash equilibrium. Namely, we now let D subscript minus I superscript I be another independent sample from all these distributions. So buyer I now just draws some sample again from the distributions. And here we even don't have to assume that the buyer knows this, because the buyer just sees whatever items are available, and out of these the buyer will choose some. But one thing that they could do, every buyer could in principle now do the following. Buyer I could buy exactly the item that they are getting in the optimal solution when their value is Vi and the other values are V minus I superscript I. And then they would get utility Vij minus Pj, but only if this item has not been sold yet. Okay, this is a difficult step. Although, yeah, it's not exactly difficult. I think what makes it difficult is the notation, but this notation is extremely helpful to then for the following steps. So what is a lower bound for the utility of buyer I? Buyer I could choose to draw an independent sample from the distributions D minus I, and then they could buy whatever item that they are getting, so let this item be now called item J. Let item J be the item that buyer I gets in the optimal solution when buyer I's value is Vi and the other buyer's values are V minus I superscript I. Then the value, the utility is of course Vij minus Pj. This is the utility from buying item J. But I'm getting only this much if this item has not been sold yet. If the item has already been sold, then I'm not buying anything, of course, or not of course. Then what this tells me is, then my utility is at least 0. So if the item has already been allocated, then this tells me don't buy anything. So once again, buyer I could, instead of now seeing what are the possible choices that I have, they could also do the following. They could draw another valuation profile from the distributions, see which is the item that I'm getting in the optimal solution with my current valuation and these hallucinated valuations. Is this item still available? If so, I could buy it. Otherwise, I'm not buying anything. The utility that you're getting this way will be at least as much as if you were, sorry, the other way around. The utility that you're getting when you take your favorite item will be at least as much as when you're following this thought experiment. And now the amazing thing is we can play with this and we can play the same tricks that we played in the context of Bayes-Nash equilibria. Namely, this will be another independent sample from the distributions, and what we will assume, the way we will work with this, is this is the actual truth, and this V that is showing up here, for example, this is not the truth. This is something hallucinated. Good. Let's go through this. Bilinearity of expectation the expected utility that buyer I is getting is at least the expectation of what I wrote up there and again, linearity of expectation, as I was saying, we can move the expectation inside there. What now about this expectation here? What does this depend on? Well, here, this depends on VI and this hallucinated thing. This also depends on VI. But all of this part does not depend on at all on the true values of the other buyers. Whereas this part here, what was this saying? This was, is item J already allocated when buyer I arrives, when buyer I is asked? This does not depend on buyer I's value because buyers 1 through I minus 1 don't even know what buyer I's value is. And this is the reason why those are actually two independent random variables, and so we can split up the expectation into the first part and the second part. Now, we again use the magic that we were using in the context of the price of anarchy of Bayes-Nash equilibria, namely we swap V minus I superscript I with V minus I because they are drawn from the same distribution. And this lets us rewrite this thing here also as the expectation of the indicator now that J is what I'm getting in the optimum times Vij minus Pj. And here we're using that the item will be available for buyer I to buy, so that only one of the buyers, or once again, that buyers 1 through I minus 1, if they don't buy the item, this is necessary for no buyer to buy the item, or maybe in a different way, this is the indicator nobody is buying the item at all. And this is the indicator nobody up to buyer I minus 1 is buying the item. And this indicator is at most this indicator, because if nobody is buying the item up to until the very end, this in particular means that nobody's buying the item up to buyer I minus 1. Good. So overall, we now get that the utility, the expected utility of buyer I will be at least take the sum over all items. What is now the expectation of this term here? Times the expectation of that other indicator. Great. So far we now have a lower bound on the expected utility of buyer I, which is this interesting term. Once again, let's see what this is saying. You could also express this, as I was saying, in different ways, but this is most convenient for what is coming up very soon. Take the sum over all items, and now you'll have the product of two expectations. The first expectation being, is this the item that buyer I is getting in the optimal solution? And if so, multiply, take Vij minus Pj. Otherwise, take 0 here. And then there's this other indicator, the expectation of, does the item not get allocated at all? So this you could also write just as the probability of the item not being allocated at all, although I'm not writing this way on purpose. Good. Now, how do we get to the overall social welfare? We now have a lower bound on the revenue, on the expected revenue. This was very easy. You might even have forgotten this by now, that we did this at the very beginning. And then we also have this lower bound on the utility. And now we first take the sum over all buyers, because the expected social welfare we can write as the expectation of the sum of the utilities plus the revenue. Good. So the expected sum of the utilities by linearity of expectation, it seems we're using linearity of expectation so many times today, I'm losing track of how often. And now we can use this lower bound for each of these individual terms. And let's now move the sum over all I further inside, because this last term here, this doesn't depend on I at all. So we might also write this as follows. Take the sum over all items j. And then take the sum over all players or buyers. Then take the expectation of this other term, which was the indicator, am I getting this item in the optimal solution, times my value minus the price. Good. How big is this last thing here? This we can also, once again, using linearity of expectation, we can write as follows. Take the expectation of the sum over all buyers, indicator j is equal to opt I of v times vij, and from that subtract also the sum over all players. The indicator, is this the item that buyer I is getting in the optimal solution, times pj. Good. Let's now see what these two things mean. This here might ring a bell, because we have seen this kind of an expression much earlier today. And let me go back there. Here it is. This was exactly the definition of the price back then. I also wrote it like this. We can say that the price for item j given valuation profile v is a half times this exact sum that we're seeing there. It's the sum over all buyers. Who is buyer I getting this item in the optimal solution? The indicator times their value. So if we now go back, we see that this here, this is exactly twice the definition of pj superscript v. And so this means, what is the expectation of 2 times pj superscript v? This is exactly 2 times pj, because we can move out the 2 by linearity of expectation, and then we get exactly the definition of the price, although the price was stated in terms of the v-tilde, but we could also state it in terms of v. Doesn't actually matter, doesn't actually make a difference. Now what about this second part here? What do we know about the sum over all buyers, the indicator that buyer I is getting item j, times pj? Okay, this we can also write as follows, because this pj, that doesn't depend on I. And now we have the sum of all these indicators. As you see, indicators are playing a very big role in this argument. We now have the sum of these indicators. Is buyer I the one who's getting item j? But what will the sum of these indicators be? The sum of these indicators will be at most 1, because at most one buyer will be getting the item. So this will be at most pj, because this sum, this will be at most 1. So we'll see here that this is at most pj. What does this give us in total? Let's maybe put a box around this, because this was all that we used for these arguments. And now this tells us that overall we are now getting at least, continuing just the calculations from above, at least the sum over all j, the expectation of this indicator, which we've not yet touched, and then there's this other term which will get to 2 times pj minus pj. So we are getting the sum over all items, the indicator, the expectation of the indicator, once again we've not yet talked about this, times pj. And what was this that we were bounding here? This was the expected sum of utilities. And after this mess, we are now at a very simple formulation. Namely, take the sum over all items. What's the probability that the item does not get sold? Times its price. Cool. And now we assemble these two things. We still have our bound for the expected revenue. We have a bound for the expected sum of utilities. And this gives us a bound on the expected social welfare. Namely, the expected social welfare will be the expected revenue plus the expected sum of the utilities. And now, what does this look like? For the revenue, we are getting the sum of the pj times the indicator, the expectation of the indicator that the item does get sold. And then, this is only a lower bound, but that's fine. We get the sum of the pj times the indicator that the item does not get sold. And here we are again. This will be exactly the sum of all these prices. And the sum of all these prices will be a half times the expected optimal social welfare. And this proves what we wanted to show. Good. So I think this looks a little intimidating when you see this for the first time, and it is also a bit surprising that all of this works out. What makes this really difficult, I think, is that we are always moving things inside expectation, then we're moving again things outside expectations. We're using linearity of expectations so many times here that I would never even dare to count it. But eventually, the argument is exactly the one that we were using also for the full information case. There, of course, everything without expectations. but the argument was the same. Any buyer can try to buy what they're getting in the optimal solution, and either they get the item, then they have a good utility, or they can't buy the item, but what happens then? For every item that they cannot buy, we get this term here, which is just revenue. So the bottom line is, from every item, you have to get a lot of welfare, either by the utility of the one who's supposed to buy it, or by the revenue of somebody else. And this is exactly where this factor half comes from, and why you wouldn't want to choose a different factor, because here we are suddenly getting twice the price minus the price. And here, if we chose a factor that was bigger than a half, then we would actually get something that is less here. Whereas here, for the revenue, we would get something that would actually be more than a half. But setting this factor to exactly a half is indeed a sweet spot here. Now you could ask, to what extent is this optimal? And indeed it is optimal in a very strong sense, because for these posted prices mechanisms, even if you have only a single item, then you cannot be better than a half. And in the lecture notes you find a very simple example that I'm not going through today, but which will help you see that if one constrains oneself to these posted prices mechanisms, then you actually cannot do better than what we're getting here in the incomplete information setting. In the full information setting, where we know these valuation functions in advance, you can do better. Although it is still an open research question of how well you can do. This completes our lecture for today. And if you found this a little messy, maybe that's for a good reason, because this is cutting-edge research. This is a paper from like now 5 years ago, but it is still what people work on nowadays. So also I've worked on very similar problems, and I've recently published a paper which actually generalizes this result in a way, although with a worse factor, but much beyond unit demand valuations. So this also works if you go beyond unit demand valuations to a class which is called fractionally subadditive, or XOS. Everything actually works the same way. I just find it a little less intuitive there. And that's why I'm restricting our attention here to these unit demand functions. But then you can even go beyond that, and you can understand any other class of valuation function. And this is what people have been doing and what people are still doing nowadays. And so the bottom line that we're taking away from this is, yes, prices can indeed coordinate markets in a way that there is the classic economic theory which tells us everything is great, we're getting away with a full welfare, but also if we assume less, if we assume ties aren't broken in our favor, if we assume that we only know the valuation distributions, even then we can still guarantee a constant fraction of the optimal social welfare. As usual, if you have any questions, please do let me know. And other than that, have a great day, stay safe, bye.